Hi, and welcome back to another episode of Next Gen Ed. We're continuing on, and we're going to do a third video about pulleys. Pulley problem number 2. The first video, we just kind of touched base on pulleys and like what they are, and like basically how we, interact with them, which is the first two on this list right here. So basically, what we're going to do is we're just going to recap all of them. Basically, the first two are from the first video, and number 3 is from the second video, obviously. Anyways, so pulleys and ropes are viewed as massless. So, basically, this rope is viewed as massless, so it technically does have some weight to it. If it was a chain, then we definitely want to take into account that. Just because it affects things a little bit more. So if it was a little denser and thicker and might affect things happening, then yeah, obviously we're going to take into account it. But for the most part, whenever you're dealing with pulleys and ropes, and it's just going to be they're negligible, in other words. So yeah, number 2, force is constant throughout the rope as a result. So basically we're just going to have one type of force for each rope. So with this force, we would probably call it F. Now with this force, throughout the whole thing, no matter how many turns it takes and everything, we're going to have a constant force as well, tension, so just T right here, and then this one would just be F. So yeah, so it's just constant tension throughout the whole rope. Anyways, so moving on, so we have number 3, the length of the rope is constant, so it has continuity. So in other words, the rope isn't stretching too much, so we just say it's like the same length. And so if it's the same length, then we can like make some equations throughout it all. So we kind of saw that when we had like L, and we set it equal to like R plus RC plus, blah blah blah. So all the distances and everything. So just to redefine the length of the rope. Like I said, we're going to start off with our basically continuity equation. So the length of the rope is going to equal, as discussed before. So we'll just write this guy in right now. This is dA. So we have RC. So I was just getting ahead of myself. RC is just going to be the constant portions of the rope. So same thing right there and right there. So yeah, and then dA, so that's going to be that distance, so the distance to the middle of the pulley, which is basically connected to the A, so that's why I'm saying it's A. So A is probably would have been like, hey, that's right there, but we're not going to think that way right now. So anyway, so it's going to be plus 2dA. So dA, and then dA right here. And then we're also going to have a chunk of the rope being pulled into this motor. So it's a little different because we got the motors now. So yeah, that's going to be plus DC. So it's going to be DC pointing that way just because the more rope it takes in, it's going to be a positive value. So anyways, and then this is going to be measured from that direction, so from the motor. So yeah, also another thing to note about the motors, so as you can see, we have these AD and AC set up. So basically we are given the acceleration of our motors. Typically that is, well, I shouldn't say typically, from an engineering standpoint, you're not going to be given that. You're going to be given like a torque or something, so you're going to have to do some of the forces and everything. So in order to simplify the problem and just do the continuity equations and whatnot, so practice more of that, we're having acceleration attached to the ropes. So obviously the heavier the blocks are, the less it's going to accelerate, like the slower it's going to accelerate in the end, so, and everything. So yeah, obviously we're not taking into account that, but we're just simplifying the problem by giving them accelerations. So but yeah, anyways, I digress. So L equals So moving on, so we have our equation to start off, and then we're going to have basically rewrite it as 2. So obviously L is going to be the same thing, and the rope constant is going to be the same thing. However, I'm going to put an initial condition. So this is basically like the final condition, after t amount of time, and then this is going to be an initial amount at t equals 0. So TC naught, DC naught, I should say. So, and then we're going to subtract our equations, just like we've always been doing in the, well, I shouldn't say always, just in the last video that we did. So it's going to be 0 equals 0 plus 2 delta A. So delta is just going to be final minus initial, so it's the change. So final minus initial, so that gives us our delta, plus delta C. So then we're going to just write that over here. So delta A equals a half delta C, and then it's going to be negative as well, because subtract it over to here and then divide by 2. So that's going to be our first equation. Technically, this is not useful right now. We do not need it. It's just kind of there for the meantime. So okay, now moving forward with it all. So basically, actually, before we move forward, let me talk about the problem in general. So like what we're trying to solve. Obviously, we need to solve something. So basically, we're solving the amount of time it takes for B to get to the edge of A. So when B is going to fall off of A in the end. So we're also going to get the velocity of how fast is B falling off A then at that point. So first thing first, we got to find out that time. So yeah, and we'll get to that. So first thing first, before all that, we just got to get our equations. Otherwise, we're just working with nothing. So we have to get our acceleration equations and then work from there. In order to get that, we're going to take the derivative of this equation. So 0, derivative of L is going to be 0, derivative of rope constant is going to be 0, it's not changing, plus 2 VA plus VC. So that's just going to be VC, or VA, it's going to equal 1/2 VC. It's going to be negative. And then just analyzing all this. So we have DA pointing that direction, but do we really want DA pointing that direction? Not really, because we want VA or DA to point that direction. And then XA, we'll call it XA. And then we want XB pointing that direction, just mainly because these two subtracted are going to get S in the end. So our length really is going to be 3 minus that then. So, but anyways, so in converting then, so we thought VA was going that direction, so VA is going to go this direction though. So if that's the case, then we're going to have VA. So we're going to substitute in for VA, negative VA in the end, because we're going from this one to the other one, like I just said. So we got to substitute it in. So when we do that, we get negative VA equals negative 1/2 VC. That makes them both positive, and then therefore our equation is just going to be VA equals 1/2 VC. Let's take the derivative of that now. So we get our acceleration equation. AA equals a half of AC AA equals half of AC AA equals, so implementing 3t squared into there, yeah, 3 halves t squared. That's going to be meters per second squared. Obviously, keep the same units. So now let's sort of implement AD over here. So then we also have AD equals basically AB. So they're going to be exactly the same. So the amount of rope that gets pulled in here is just going to be the amount of, amount the rope that has moved here then. It makes perfect sense. And then if you take the derivatives twice, you get the acceleration equation. So yeah. A B then is going to equal AD. AD is just a half meters per second squared. Anyways, so we're going to take the integrals. Okay, great. Let's now start taking integrals. So AA, let's get that as a XA, but as a function of time. So AA, that's 3 halves t squared. So integrate. And that's going to be VA equals, so the integral of this is going to be, so this turns to t cubed, just over 2. So just because you're going to change this to a 3 and then you divide by 3, so that cancels out with a 3 in the front. And then let's take another integral. We're going to get XA then. So it's all starting from rest as well, so it would be like plus 0. So for our initial condition, by the way. So if you're wondering about that whole plus C scenario, it's plus 0 because we're assuming everything starts from rest. So it's typically most of our problems anyways that you do. So, but anyways, so same thing. We're saying that's the initial spots as well. So we're going to say the initial is 0 from there. Then if we take our integral, so this is going to be t to the 4th. So t to the 4th. So we're going to divide by 4, so then we get over 8. So, and then that's meters in the end. So let's do the same thing, but AB, it's just a half. So we're going to take the integral then. And that's going to lead to VB equals, so it's going to be a half t. Obviously it's going to be plus 0, just like I explained. They're starting from the rest. So we're going to do another integral. So when we do that, it's going to be t squared, and then divide by that, so then we get over 4 meters. So cool. So let's now start up our S equation. So S is going to equal 3. So we start with 3, and then we're going to minus. So the more XB gains, it's going to be shrinking. The more X A gains, it's going to be shrinking as well. So minus xb. So that's s naught really, this thing. So the 3. But anyways, so minus xa as well. So this would be 3 minus, so p squared over 4 minus t to the 4th over 8. And then we're going to set it equal to 0. So we're setting it equal to 0 because it's going to be right as it's falling off. So that's going to give us our time in the end. So rearranging 0 equals, then we're going to put t to the 4th at the beginning, t squared middle still, and then our constant is going to be at the end. So we're going to multiply everything by 8 as well, negative 8 to be honest, just because we want positives right there. So negative 8 to this whole thing right here. So we get, like I just said, this one to start off, so that's going to be just t to the 4th plus 2t squared. So then minus 24. Okay, and then that will come out to basically t squared minus t squared minus. So I put minus signs just because you can easily cross them and make a plus sign. So why write more? So, but anyways, well, why erase? I should say. Anyways, so it's going to be negative 24, what they have to multiply to, and then they add to that. So what is that? 6 and 4. That's going to be a good one for this one. So it's going to be a positive 6, and then minus 4, I believe, yeah. So here we go. So multiply them, you get negative. Add them, you get positive 2. Okay, cool. You know, and then this is not going to equal 0. So t squared, this is just, it's just going to be 6 and up. So this is not going to be of any use. It's this one in the end. So, so 0. So this will be t squared equals 4. So then t equals plus or minus the square root of 4. So it's 2. So it's not going to be plus or minus. We're just going to say plus because negative time does not make any sense. So 2 seconds. So at 2 seconds is when it's going to fall off. So t equals 2. Okay, so we're almost done. So we found out the time it takes for it to be about to fall off, right at the edge. And then we have our S equation. So we're going to find out what the velocity is. So Vs. Vs is the main thing we're wondering because it's kind of, hey, what is it relative to the top block falling off the bottom block, you know? So we take the derivative of 3, that gives us 0. So, and then negative Vb minus Va. So, and that's going to be Vs equals, so I erased them just now, but backtracking, that's negative t cubed over 2, so, well, I guess a, I switched them around, I guess, and then the integral that was just t over 2 minus t over 2. So now let's just implement the 2 in it all for t. So VS at 2 equals, so plug in a 2 here, that literally just gets rid of the 2's in the denominators. So really makes it t squared then, so minus 4 minus, and then that's just going to be 1, 2 over 2. That gives us -5 meters per second. And then that's our answer, Vs equals -5 meters per second. So this is a pretty cool problem. Just gonna have to dissect it all. So gotta get this equation, or S equation, that's a big portion of it, and we also have to get comfortable with our continuity equations, well, the equations that we get from the length of the rope being constant, in other words. So, but yeah, hopefully this was a great video for you and helped you out, and I guess I'll just see you in the next video.